Welcome, dear friends. Am I audible to you? Okay, thanks, Saurabh. Thank you. We would be solving one numerical, and hopefully you are accompanied by the notebook and steam tables. You are carrying your notebooks and steam tables with you. So you need to take down. I would be dictating the numerical and also writing it on the board. Okay. So allow me a minute to share my whiteboard. Okay, dear friends, let us start solving a numerical. I would be dictating the question for you. I will also be writing it on the board simultaneously. So the question is as follows. It is a numerical on Rankine cycle, which we discussed yesterday. The question is as follows. The steam, which is at 20 bar, steam, which is at 20 bar, pressure, and 360 degree centigrade temperature. 350 degree will take first at us 350 degree centigrade temperature. Is expanded to 0.08 bar. Okay. So before I dictate the complete question, I am asking you one sub question. What is the saturation temperature of the steam at 20 bar? What is the saturation temperature? From the steam tables, you'd let me know this. What is the saturation temperature of the steam at 20 bar? You can write down the answer in the questions column. Any answers? What is the saturation temperature? Temperature. What is the saturation temperature? Gargi is right. Kamlesh is right. Sharvari, you are not written temperature. I guess you are written the enthalpy value. Right. Now it is right, Sharvari. Aditya is right. Okay. So what is the meaning now that the steam is at yeah, correct, Ananta. Steam is at 20 bar 350 degrees centigrade. So what is the meaning of this? What you need to comment on the quality of the steam. The steam is at 20 bar and 350 degrees centigrade. So quickly comment on the quality of the steam. Ananta, Aditya, Neha, Ganesh. What you are written, Ganesh? Yeah, Gargi, it's correct. Ganesh, what you are written 365? I'm not following this. Yeah, right, Rushali. So the meaning is the steam which is given to you, okay, in the problem is superheated steam. Okay, why is it superheated? It is superheated because the steam would start, the boiling point of the steam is 212 degrees centigrade. Okay, the boiling point of steam is 212.2 or 0.4 degrees centigrade. Okay, and the given steam is at a temperature which is higher than 212. Okay, it means that the given steam is superheated steam. Okay, now this steam is expanded to zero point 0.08 bar. Okay, the steam is expanded to 0.08 bar, that is given in a power plant. In the power plant is expanded to 0.08 bar in the power plant. Okay, so assuming the ideal Rankine cycle, assuming the ideal Rankine cycle, you are supposed to calculate specific turbine work, specific pump work, the heat added per kg of steam, and finally the Rankine cycle efficiency. Okay, you need to assume that the steam becomes saturated liquid. You need to assume that steam becomes saturated liquid after condensation. After condensation, okay, that you have to assume. So the first step in solving the problem is, have you taken down this problem, all of you? Whether you have copied down this problem, yeah, you will require to, yeah, thank you, Gargi. You need to copy this down so that you will follow it step by step. Okay. So now let me draw the temperature entropy diagram. I told you that for solving this problem, you need to be very clear on what is given, and that clarity comes if you represent this cycle on a temperature entropy diagram. Okay. So I'm now going to represent this cycle on a temperature entropy diagram. Temperature entropy diagram. Okay. Right. So this is a vapor dome which I have drawn. Okay. And this, what is this which I have drawn now? Tell me, what is this which I have drawn? What is that I have drawn on the vapor dome? It is a constant pressure line. It is a constant pressure line. And what pressure we are talking about? What is the pressure we are talking about? The boiler pressure is what? How much is the boiler pressure? Yeah, correct. So boiler pressure is 20 bar. Okay. So 20 bar. So this is 20 bar. This is 20 bar. Okay. Suppose this is A and B. Tell me the temperatures at TA and temperatures at TB. What is the temperature at TA? What is the temperature at TB? What is the temperature at TA? Look at the diagram and tell me what is the temperature at TA. Correct. Gargi is right. The temperature is 212.4 degrees centigrade. Okay. That is the temperature. All right. And compressors is right. So the given steam, let us say that this is your 0.2. Okay. Let us say that this is your 0.1. Okay. So what is T2 then with my notations? What would be T2? Tell me what is T2? How much is T2? Look at the diagram and tell me how much is T2. Look at the diagram and tell me how much is T2. T2, Neha. No, T2. Yeah, correct. Neha is correct. T2 is 350 degrees centigrade. T2 is 350 degree centigrade. Okay. So this temperature would be 350 degrees centigrade. Now what I am doing is that I am be representing the process of expansion on the Rankine cycle. So this process of expansion, you know that it would be a vertical line. Okay. Let me try drawing a vertical line here. This is a vertical line. Okay, assume this is to be a vertical line. Okay, there is difficulty drawing a vertical line on this blackboard, but assume this line which I have drawn 2, 3 to be a vertical line. Okay, so can you find the enthalpy? Can you find the enthalpy H2 from the steam tables? Okay, so for finding the enthalpy H2 from the steam tables, you need to refer to the superheated steam table. There is a superheated steam table. There is a superheated steam column in the superheated steam table. In your steam tables, you will have superheated steam column. Okay, and in that superheated steam table, look for the pressure of 20 bar and 350 degrees centigrade, and tell me the value of enthalpy at 20 bar and 350 degrees centigrade. Tell me the value of enthalpy H2. 20 bar 350 degrees centigrade. Tell me the value of enthalpy H2. There is a superheated steam table. In the steam table, you will have saturated table and superheated steam table columns. Okay. So I don't know which table you are using, but enthalpy value is not that low, Kamlesh. Enthalpy, I am talking about enthalpy, not entropy. So superheated steam table you need to refer to. So 20 bar 350 degrees centigrade, the value of enthalpy is around 3137. Are you able to look at that? Anybody of you? At 20 bar and 350 degrees centigrade, the value is 3137. Okay. Yes, Aditya is closer. So Aditya is right. 3137 or 3138, whatever, right? Yes. So unit is what? The unit would be kilojoules per kg. Please note. Kilojoules per kg. 3137 kilojoules per kg would be so Neha, Kamlesh, Aditya have got these values. Others also please try to look at this value. Neha, you have slightly different value. At 350 degrees centigrade, the value is 3137. Closer to that. Okay. 3138 is also all right. So Aditya and Kamlesh are on the track. Uh, look for the enthalpy value, specific enthalpy value. Because it is specific enthalpy, its unit is kilojoules per kg. So others, please try to get the values of enthalpy from the steam tables. I hope you are having the steam tables with you. If you are not having the physical steam tables, at least try to get the values online. Okay. Others, I want others to write down this value. Okay, Ananta has got this. Yuraj, you just check. Yeah, Yuraj has got it. Ananta has got it. Rushali, Gargi, Kunal, Nikhil Pardesi, Saurabh Jadhav. Tejas has got it. Okay. Okay, Rushali has got it. Now, what is important for you is if I want to find the turbine work, okay. So what would be turbine work expression? Specific turbine work expression per kg. Look at my diagram and tell me what is the turbine work expression. So the turbine work expression would be H2 minus H3, okay, per kg, where M is okay. So you already know H2 now. From the steam table you have obtained that H2 value. So we need to figure out H3 value, okay. So how do you find H3? So what is the state? What is the state of, look at my diagram and tell me the state of steam at 3. What is the state of steam at 3? State, not process. What is the state of the steam at 3? Whether it is, no, it is not liquid, Sharvari. It is not liquid. Kamlesh, it is not superheated. Yeah, Neha is right. It is wet steam. It is a wet steam. Ananta, it is not dry, it is wet steam. Okay. So it is a wet steam. And what is the pressure of that? It is slightly, it's almost dry steam. Please note, it is closer to the saturation curve. It is almost dry steam. So it is a wet steam after expansion, almost dry. Okay, almost dry, I would say. Right? And what is the pressure of that steam? And what is the pressure, at which pressure it is there? What is the pressure of the steam at 3? What is the pressure of the steam at 3? Tell me, what is the pressure of the steam at 3? Ananta, Rushali, Gargi, Neha, Kamlesh, Tejas, Sharvari, Yuvraj. What is the pressure at 3? Look at the diagram. See, what does the turbine do? The turbine would expand the steam from the boiler pressure up to the condenser pressure. Okay, and the condenser pressure is given as 0.08 bar. 0.08 bar. Okay, so the steam at 3 is at 0.08 bar. Is this okay? The steam at 3 is at 0.08 bar. Okay, 0.08 or 0.8. How much is that? It is 0.08, not 0.8. Yeah. And how to find the enthalpy of the wet steam? What is the expression we use? Okay, Gargi, look at this. What happens in the turbine? The steam enters the steam turbine superheated at a superheated state. That is, in my diagram, it enters at state 2. Now, what does the turbine do? The turbine would expand the steam from the pressure P2 up to the pressure P3. What is the pressure P2? The pressure P2 is a boiler pressure and pressure P3 is the condenser pressure. So the steam turbine would expand the steam in this case from 20 bar, which is a boiler pressure, up to 0.08 bar, which is the condenser pressure. Is this okay? Right? So the steam at state 3 would be at 0.08 bar. The steam at state 3 would be at 0.08 bar, that is at condenser pressure. That is, it would be at a condenser pressure line. So let me draw the condenser pressure line on this. The condenser pressure line is this. This is the condenser pressure line and the pressure is 0.08 bar. 0.08 bar. So how do you find the enthalpy at state 3? So you find the enthalpy at state 3. H3 is the enthalpy of wet steam, which is nothing but HF plus X3 HFG, where X3 is the dryness fraction at 3, where X3 is the dryness fraction of the steam at 3, dryness fraction at state 3, that is at the turbine outlet, or condenser inlet, which is same thing. Okay, so we need to find the enthalpy. Now, how do you find H3 from the steam tables? So look for the value of HF at 0.08 bar and tell me that value. Tell me the value of HF at 0.08 bar and tell me the value of HFG at 0.08 bar. Tell me the value of HF at 0.08 bar and HFG at 0.08 bar from the steam tables. Point 0.08 bar HF and HFG. So the value of HF is 173.9 and HFG is 2403.2, which is correct. Anamta, Nikhil and Neha, they have answered it correctly. Okay, Sharwari. So the answer is if you look at the steam tables, you'll find that the value of HF is 173.9 and value of HFG is 2403.1. 2403.1. Okay. So let us write down these values. So the values are HF is from the steam tables. So H3 will be HF, which is 173.9 plus X3 into HFG, which is 2403.1 or 2, whatever you have with you. Okay, doesn't matter much. So X3. Now, if I want to find what it means is that if I want to find H3 or if I want to find the turbine work, then I need to figure out the dryness fraction at 3. Yes or no? If I want to find H3, then I need to figure out the dryness fraction at 3. Whether this is clear? Do you agree with me that if I want to find H3, I need to figure out the dryness fraction at 3? In order to find H3, I need to find the dryness fraction at 3. Whether this is clear? Whether this question is clear? Yeah. Okay. So Kamlesh Ananta is saying yes. So let me, yeah, Yuraj. So how do I find the dryness fraction at 3? So in order to find the dryness fraction at 3, we make use of the fact that the process process 2-3 is isentropic. Okay. In order to find the dryness fraction at 3, what we do is we make use of the fact that the process 2-3 is isentropic, meaning the entropy at 2 is equal to entropy at 3. Is this okay? The entropy at 2 is equal to entropy at 3. Why is that so? That is because the process 2-3 in my case, which is the process of expansion, it is an isentropic expansion. Okay, ideally speaking, in the turbine, the process of expansion in the Rankine cycle is isentropic expansion. Okay, now what is the state at 2? What is the state of the steam at 2? What is the state of the steam at 2? What is the state of the steam at 2? Yuraj? You, it is, Anamta, it is not liquid, it is superheated. It is superheated. Okay, so Sharwari is right, Neha, Yuraj are right, Pranav is right. It is superheated steam. Okay, so it means that, and what is the pressure of the steam at 2? What is the pressure of the steam at 2? It is 20 bar, Pranav. Correct. It is 20 bar. And what is the temperature of the steam at 2? Kamlesh? Yeah, correct. It is 350 degrees centigrade. Okay. So this is S2. This is S2. Okay. Now tell me what is the state of the steam at 3? Rushali. What is the state of the steam at 3? What is the state of the steam at 3? Kamlesh, it is not dry steam. Neha, yes, it is right. It is a wet steam. It is almost dry, but it is wet steam. Yeah. It is wet steam. So it is wet steam. And what is the pressure of the steam at 3? What is the pressure of the steam at 3? Correct. Yeah, right, Neha. So it is 0.08 bar. Okay. Okay. And you know that this entropy of superheated steam, which is at 20 bar 350 degrees centigrade, is equal to the entropy of the wet steam, which is at 0.08 bar. Okay. So let me rewrite this equation. So this is S superheated. From the steam tables, we need to find the value at 20 bar 350 degrees centigrade is equal to SF plus X times of SFG. Okay, at 0.08 bar, at 0.08 bar, and mind well that SFG is nothing but SG minus SF. SG minus SF at, so S at 20 bar 350 degrees centigrade is equal to SF at 0.08 into SG at 0.08 bar minus SF at 0.08 bar. Okay. Whether this is understood? Whether this equation is understood? How I came to this equation? This equation which I have written in the block, whether this is followed? Yes or no? Pranav, Kamlesh has followed, Yuvraj has followed. Others, whether they have followed this, what I have done? What I have done here, see, this is a very important step in solving the numerical. So Kamlesh, Yuvraj and Sharvari are saying that they have followed. I want others to say that they have followed. Ananta has understood this. Neha has understood this. Rushali wants me to repeat. Okay, Rushali. What are we doing here? Okay, we are doing a trick to find the dryness fraction at the state 3. What we are doing here is we are doing a trick to find the dryness fraction at state 3. Now, what is a trick? We make use of the fact that the process 2 to 3, which is the Rankine cycle, is an isentropic expansion process. I mean to say that the phenomena of expansion which is happening in the turbine, steam turbine, is assumed to be isentropic in case of ideal cycle, which is the Rankine cycle. Okay, so the process 2 to 3, using my nomenclatures, the process 2 to 3 is an isentropic expansion, meaning entropy before expansion is equal to entropy after expansion. So entropy before expansion is S2, entropy after expansion is S3. Now entropy before expansion is the entropy of superheated steam from the diagram which I had drawn. Entropy of the steam before expansion, that is at the inlet to the turbine, is the entropy of superheated steam whose pressure is given to be 20 bar and temperature is given to be 350 degrees centigrade. Okay, now it is expected that after expansion the steam becomes slightly wet. Okay, it's almost dry but slightly wet. So the entropy of the steam after expansion is the entropy of the wet steam, and it is now at a lower pressure which is at 0.08 bar. Okay, It means entropy at 20 bar 350 degrees centigrade is equal to SF plus X times of Sg minus Sf. Okay, Sg minus Sf. What is this expression? This expression is the entropy of wet steam. And what is the pressure of this? The pressure is 0.08 bar. Right? So now what we need to do is that from the steam tables, find the entropy at 20 bar 350 degrees centigrade, find the Sf value at 0.08 bar, find the Sg value at 0.08 bar, and from that you can get the value of X3. Is this understood? Is this understood? Rushali? Okay, Rushali has understood this. Thank you, Rushali. So now let us write down these values, SF, SFG values, and calculate the value of X3. So the value of SF at 0.08 bar, if you look at the values, you will find that that value is 0.593. 0.593. 0.593. Sometimes here I have the steam table which directly has the values of SFG, but sometimes if you don't have the value of SFG directly, then you need to do the subtraction of as SG minus SFG. So I have the value, so I would directly write the value of SFG as 7.636. 7.636. Okay, those who don't have the value of SFG directly, they can write the value of SG from the steam tables. That value would be around 8.229, and SF value is 0.593. Okay, that subtraction would give you the value of 7.696, 636. Okay, and from the superheated steam table. You need to figure out the value of entropy at 20 bar and 350 degrees centigrade. Okay. So 20 bar and 350 degrees centigrade, if you look up for the value of entropy, you'll find that that value is 6.956. 6.956. 6.956. Okay. You need to substitute these values and you'll get the value of dryness fraction. Do this. Please do this and tell me the value of dryness fraction. It would be some value of 0.9 or something, I guess. Ananta, you need to check your value. It is wrong. Okay, so Neha appears to have got the answer. I just will be cross-checking this. Okay, Ananta has also got the same answer, so it is probably right. So the dryness fraction, just work out the dryness fraction. Others also work out the dryness fraction. Others also. Okay, Pranav has also got it right. Pranav, Anamta, and Neha have got the values of dryness fraction as 0.83, which is correct. Okay, so let us take this value of 0.83 and let me put this value of 0.83 here to find the enthalpy. Okay, so in my H3 expression, I would be putting the value of 0.83 and I will be calculating the enthalpy H3. So now you tell me the value of H3. Pranav, tell me the value of H3. X3 value is 0.83. So you need to substitute the value of X3 as 0.83 and get the value of enthalpy H3. Substitute the value of X3 as 0.83 and find the value of enthalpy H3. Okay, so Neha has got that as 2168. Others, yeah, okay. So all of you are getting this value 2168. So once you get the value of 2168, right? Now you need to find the turbine work. So calculate the turbine work now. Calculate the turbine work. Calculate the turbine work. So turbine work would be H2 minus H3. Turbine work would be H2 minus H3. So how much is that value? Okay, so Pranav has given me the answer. That value is around 968 kilojoules per kg. Okay, 968 kilojoules per kg. So for every kg of the steam generated by the boiler, the turbine would produce 968 kilojoules of turbine work. Okay, the meaning is for every kg of the steam which is generated by the boiler, the turbine would produce 968 kilojoules of work. Right. Now we have figured out what is the turbine work. Now we need to figure out what is the pump work. And how do you find the pump work now? Where is the pump work? So this is point 4. Look at the diagram now and look at this vertical which I have drawn. So the pump work, please note, pump work is nothing but H1 minus H4. What you know is, you know the value of H4, but you don't know the value of H1. Okay. So in order to find pump work, we will use another trick. Now listen to this carefully. The trick to find the pump work. How do you find the pump work? Okay. Pump work value would be negligibly small, but from the examination perspective, you need to work out that value and by the method which I am suggesting. Now pump, whether it is an open system or closed system, the pump is an open system. Okay. Pump is an open system, and the steady flow work, assuming it to be a steady flow, can be calculated as VDP integral, which is nothing but V F into pressure of boiler minus pressure of condenser. Please note this. Pressure of boiler in pressure of condenser, where pressure has to be in kilopascals and this has to be in meter cube per kg if I want the answer in kilojoules per kg. Okay. I am sure that you are comfortable with the units. Okay, if you are not, just revise this. So in order to find the pump work, we will make use of this equation. V of, that is, it is integral of VDP work because it is an open system, right? And you need to find this pump work as V into delta P. Now boiler pressure is 20 bar. 20 bar. Okay. 1 bar is 100 kilopascals. 1 bar is 100 kilopascals. Condenser pressure is 0.08 bar. Okay. So, and what is the value of Vf at state 1? That is at the entry to the pump, at the entry to the pump, which is state 1. So what is the pressure at state 1? What is the pressure at state 1? Any answers? No. Pressure at state 1. Sorry. Not 1. Sorry. I'm sorry. It is my mistake. The entry to the pump is 4, not 1. Entry to the pump is at, see, this is a condensation. 3 to 4 is condensation. So the entry to the pump is 4 and not 1. So by mistake I had written it as 1. So entry to the pump is state 4. Okay. And hence I need to find the pressure at state 4. What is the pressure at state 4? The pressure is 0.08 bar. Okay. So from the steam table, look for the value of Vf at 0.08 bar. From the steam table, look for the value of Vf, specific volume Vf at 0.08 bar. So Vf at 0.08 bar would be equal to 0.001 approximately. Okay. You'll always find that this value is always closer to this. So no need of seeing the steam tables also. You can straight away, for the values which we are dealing with, you can straight away write Vf as 0.001 meter cube per kg. Okay, so if I put the value as point, so I'll put the value of Vf as 0.001 meter cube per kg. The boiler pressure as 20 into 100 and condenser pressure as 0.08 into 100, and that will give me the value of the pump work. So tell me the value of pump work, how much is that? And it's valued in kilojoules per kg. So it is approximately 2, correct? It is approximately 2. Compare this value with the turbine work. So the turbine work would be much greater than the pump work. So the turbine work was how much? The turbine work which we had obtained was, I guess, 968. Okay, turbine work was 968 and the pump work is about 2. So pump work is negligibly small, and that is an advantage of the Rankine cycle, that you will require pump work which is very small, and hence the net work would be substantially higher. Net work, which is turbine work minus pump work, would be substantially higher. Okay, this is a very important advantage of the Rankine cycle. Okay, now find out. So once you get this pump work, you can figure out H1. H1. Okay, what is H1? Look at the diagram. Look at the diagram. H1 is H4 plus pump work. Do you agree with me? Look at this expression. Okay, you have calculated pump work as 2 kilojoules per kg. This H4 can be obtained from the steam tables. How to find H4 from the steam tables? H4 is at what pressure? H4 is HF. It is a liquid. H4 is on the liquid line now. HF at 0.08 bar. H4 is a liquid, so we need to look for the value of HF, not HF plus XHFG. Okay, it is on the liquid line, so it is HF at 0.08 bar. Okay, so look for the value of HF at 0.08 bar. 0.08 bar. Look for the value of HF at 0.08 bar and convince yourselves that that value is 173.9. That value is 173.9. Okay, so it means this value is 173.9. So H1 would be how much? So how much would be H1? How much would be H1? So H1 would be 175.9, right? Yes or no? So H1 would be, this is 173.9 and pump work is 2. So H1 would be 175.9. Is this followed? H1 would be 175.9. And once you get H1, you can find the heat supplied. What is the heat supplied? Look at the diagram. It is H2 minus H1. It is H2 minus H1. Okay. So the heat supplied is H2 minus H1. How much was H2? H2 is 3137 and H1 is 175.9. Okay. So write this again. Okay, heat supplied is H2 minus H1. Any confusion regarding this, that the heat supplied is H2 minus H1? H2 minus H1. Okay. So H2 is, how much was H2? H2 is 3137. And this was 175.9. Okay, so this gives you around 2961. Around 2961 kilojoules per kg is the heat supply. And how much is the net work? Net work is turbine work minus pump work. Okay, and how much was that? Turbine work was 968. Okay, 968 minus 2, so this is 966. Okay, so the efficiency of the Rankine cycle would be net work upon the heat supplied. That is, net work is 966 upon 2961 into 100%. So how much percent is that? 33%. Okay. All of you are getting it as 33? Okay. How many of you have not followed this problem? How many of you have not followed this problem? Okay, Ganesh is getting 33. Akanksha is also getting it right. Anybody who has not followed this? Pranav has got it right. Rushali has also got it. Gargi has got it. Anybody who has Madhuri Shinde has got it. Anybody who has not followed this? The procedure, okay. Numbers apart, numbers you can calculate on your own. But the steps which I had used for solving this, Anamta has understood this. So, all right, Rushali, not exactly 33 is all right. I am writing the approximate values. You can write the exact values, whatever you get. Nikhil has understood this. See, let me write down the steps for those who are shy of asking this. Let me write down the steps of solving this. What you did is, let me just discuss the steps, not write it down. I had drawn the Rankine cycle first on the temperature entropy diagram. Then, knowing the pressure and temperature at the entry to the steam turbine, this is the entry to the steam turbine, which is the exit of the boiler. This I had used to find the enthalpy from the superheated steam tables. So I got the enthalpy of the steam which is entering the steam turbine. Then I need to find the enthalpy of the steam which is leaving the steam turbine, for which I need to find the dryness fraction of the steam at the exit of the steam turbine. For finding the dryness fraction of the steam at the exit of the steam turbine, I make use of the fact that this process 2 to 3 is isentropic. The process 2 to 3 is isentropic, meaning the entropy of the superheated steam and enthalpy of the wet steam is the same. So knowing this fact that the entropy of the superheated steam and wet steam is the same, you can find the only unknown in this equation would be the dryness fraction. Once you get that dryness fraction x3, put this dryness fraction value to help you determine the enthalpy at 3. That is, H3 is HF plus X3 HFG. Okay. This way you get the enthalpy at 3. Enthalpy at 4 can be easily found out because it is at the condenser pressure line. The pressure is 0.08 bar given, and condensate is assumed to be on the F line, that is a saturated liquid line. So for finding the value of H4, what we need to do is that just look at the steam tables at 0.08 bar and the pressure and the value of HF. So H4 you will straight away get. You don't know H1, but you will need H1. But before that, you need to find the pump work. Pump work, because it is an open system, is the V delta P work. V means the specific volume at V, that 0.4. So specific volume at 4 means Vf at 4 from the steam table. You'll find that this value is always 0.001. So you can take that value as 0.001 Vf and multiply it with the pressure difference, that is the boiler pressure, and condenser pressure. Mind well that when you multiply with the pressure difference, convert this bar to kilopascals. Okay, if you want the answers in kilojoules. So convert this bars to kilopascals. So that subtraction 20 bar minus 0.08 bar into 100 into specific volume would give you the pump work. Once you get the pump work, look at this. You have H4 plus pump work will give you a new enthalpy H1. So H4 plus pump work is H1. This way you get H1. Once you get H1, which is the entry to the boiler, and you have already known the exit of the boiler. So H2 minus H1 is the heat added in the boiler. Okay. So that is the denominator of the expression of the Rankine cycle efficiency. H2 minus H1 is the denominator of the expression of the Rankine cycle efficiency. Okay. And that denominator, there is a heat supplied. In this case, it comes as 2961. And the numerator is the net work output of the power plant, which is the turbine work minus pump work. And that is in the numerator. The ratio of the two would give you the Rankine cycle efficiency. Okay. I hope you have followed this. Have you understood this now? Hopefully the class has followed this. Okay, similarly, you can find the steam rate and heat rate for this problem also. That I will give it as a homework. So for the same problem, you need to find the steam rate and the heat rate for the same problem. Okay. Okay, thanks for those who are listening attentively. I'm sure they have benefited from this lecture. Okay, others who are less attentive, they need to brush up their concepts at home, okay, and revise those concepts. So thanks for being online. Have a good day. Okay, bye for now.